We're going to talk about taking measurements in electronic circuits using voltmeters and ammeters. How do we use them? How do we hook them up? What does it mean to be an ideal ammeter or a voltmeter? And we'll look at some examples and see how they affect the circuit. If we're trying to measure the potential difference across a device with a voltmeter, how would we hook it up? We know from our rules of series and parallel electrical devices, when devices are hooked up in parallel, the electric potential difference is the same across each device in parallel. So if we're measuring the potential difference across resistor R2 in our circuit here with a voltmeter, we would hook it up in parallel with R2. Our voltmeter is hooked up in parallel with R2. It should have the same potential difference across it that resistor R2 has. Now, the problem is when we hook up something to our circuit, we change our circuit a little bit. We know that the potential difference across R2 is equal to the current through that resistor times its resistance, V equals IR. When we hook up our voltmeter, if some of the current takes the path through the voltmeter instead of going through R2, we've changed the voltage across R2. What we're measuring with our voltmeter hooked up in parallel to R2 is not the voltage across R2 when the voltmeter is not hooked up in the system. Because as soon as we hooked it up, we've changed the flow of current, we've changed the circuit, and we've got a slightly different voltage on R2 now. There's a rule in physics that says the act of measuring something actually disturbs it. So you can never measure something exactly, because every time you reach in to measure it, you have to disturb the system slightly in order to take that measurement. Well, what would disturb this system as little as possible? How could we limit the current going through that voltmeter, make it as small as possible? We don't want any current to go through there. We want all the current to go through R2 and none to go through the voltmeter. That's called an ideal voltmeter, and that would have an infinite internal resistance. R internal equals infinity for an ideal voltmeter. No current goes through an ideal voltmeter. It all goes through the resistor it's hooked up to in parallel. In the real world, we don't have voltmeters with infinite internal resistance, but they are pretty high. And so a really good voltmeter will have a very high internal resistance, and it will have very little effect on the circuit it's measuring, but it always has a little bit of an effect. If we want to measure the current through a device, we know from our rules of series and parallel electrical devices that the current is the same through every device in series. So if we want our ammeter to measure the current through resistor R2, we would hook it up in series with R2, and then we would know that whatever current is going through R2 is also going through our ammeter. That means I have to disconnect some of the wires from my circuit. Remember, when I hooked up my voltmeter, I could just reach in and clip the voltmeter on to resistor R2 in parallel to it. That was easy. But now, to measure current, I need it in series with R2. So I have to disconnect the wire that comes out of R2 and goes into R3 and hook it up through the ammeter, like this. The current that comes out of R2 doesn't have a choice. It's in series with the ammeter. It has to go through the ammeter. And so my ammeter is reading the exact same current that's going through R2. But there's a problem. I don't normally have an ammeter hooked up in my circuit. I normally just have resistors R1, R2, and R3. And I want to know how much current is going through R2. So I've put an ammeter into my system. I've changed the circuit a little bit. And that might change the current flowing in the circuit. So although I know I'm measuring the current through R2 right now with the ammeter in series with R2, it may not be the exact same current that flows through R2 when the ammeter's not in the circuit. The act of putting the ammeter in the circuit may have changed the current. How can we minimize the effect of the ammeter on the circuit? And what would we do to design an ideal ammeter? We want that ammeter to have as small a resistance as possible, so when we put it into our circuit, it doesn't change the current flowing in the circuit. An ideal ammeter has 0 internal resistance. So an ideal ammeter does not affect the circuit at all. It has 0 internal resistance. And in the real world, ammeters have very low internal resistance and have minimal effect on the circuit we're measuring. Let's take a look at this example. We have a simple circuit here with 3 resistors and a battery. We want to measure the voltage across one of the resistors and the current through another one. The meters are hooked up, as you see here. Go ahead and solve for the readings on these 2 ideal meters. I'm going to work through it now. I spot right off the bat that I have 2 resistors in parallel, and so that's an equivalent resistance of 1.5 ohms. 1 over 2 plus 1 over 6, and then I take 1 over that, and I got 1.5 ohms. And then I spot that 1.5 ohm equivalent resistance is in series with my 4.5 ohm. So this equivalent circuit would look something like this. So my current is 2 amps. Working backwards, I see that this would be my current coming out of my battery, 2 amps. And when it gets to the junction, I'll call that junction A, it splits. Part of it goes through the 6 ohm resistor and part goes through the 2 ohm resistor. That means that the current going through the 6 ohm resistor, 0.5 amps, and the current going through the 2 ohm resistor is 1.5 amps. So our voltmeter is going to read I times R (9 volts), and our ammeter is going to read 0.5 amps. Now, just for the heck of it, let's switch our meters. We'll put the ammeter where the voltmeter was and the voltmeter where the ammeter was. Now I know you're taking physics 4b, and you would never hook up an ammeter and a voltmeter like this in a circuit. But maybe somebody did, and you're going to tell me now what those 2 meters read. Let's work through it and see what's going on in this circuit. An ideal ammeter has 0 internal resistance. So there is a 0 resistance path right here for the current to flow through that ammeter. And that's called a short. No current will go through the 4.5 ohm resistor if there's a zero resistance path to go through. So I'm going to redraw my circuit. Nothing is going through that resistor. It's all going through the ammeter. I have a 2 ohm resistor here. And what about my voltmeter? My voltmeter acts like an infinite resistance. That means there's an open circuit over here. There's no path for the current to get through that voltmeter. It's an open circuit, an infinite resistance. So I can remove that whole branch from the circuit. No current is flowing through the 6 ohm resistor. And my circuit looks like this. So I have a current of 6 amps flowing through my circuit. And let's see what the meters read. We know all 6 amps flows up through this meter and out the other side. So our ammeter reads 6 amps. We know there's no current flowing through the 6 ohm resistor, so all the current takes this path. And the voltmeter is hooked up, one end of our voltmeter is hooked up here, and the other side of our voltmeter is at this potential, but there's no current coming through the 6 ohm resistor. If there's no current through that resistor, there's no potential drop across it because V equals IR. The potential drop across a resistor is the current times the resistance. If I is 0, there's no potential drop across that resistor. So this is really hooked up over here. It's the same thing as if it was hooked up over there. And the potential difference between those 2 points, the green and the blue, is equal to I times R, the current times that 2 ohm resistor. So our voltmeter is reading 12 volts. We could actually trace these lines back even farther. The green represents an equipotential surface. We could call that 0 volts if we want to. And the blue, let's trace it around. The blue, there's a 0 resistance path through this ammeter, so that doesn't change the potential at all. This is the top of the battery, 12 volts. So if our voltmeter is hooked up anywhere on that blue line with one of its leads and anywhere on the green line with the other lead, it's going to read a potential difference of 12 volts because one would be hooked up to the 0 volt line and one would be hooked up to 12 volts.